Welcome to video lecture F4. This one is on similarity of matrices. I'll be your escort, Tom Roby, and here are the outline and objectives. We'll define the notion of similar matrices and show that similar matrices have the same eigenvalues, in fact, the same multiset of eigenvalues with all the same multiplicities. And then we'll define the algebraic multiplicity of an eigenvalue carefully. It's just its multiplicity is a root of the characteristic polynomial, but I didn't say that before. Okay, so here's the critical definition. We call two matrices similar. A and B are similar if there exists an invertible matrix P such that A equals PBP inverse. And because we've used the twiddle sign sometimes for row reduction operations, I want to distinguish this one. So I'm going to write this is the character that's often used for similarity, for example, when you take geometry in high school. It's used for many kinds of things that are like similar in mathematics. But so in this case, I'll put a little s above it just so that we can keep it straight. Okay, so we'll call two the matrices similar if they satisfy this condition. And here's an example. So remember that maybe I haven't shown this example. We've done this example before in some form. If I have the matrix 1, 2, 5, 4, then it turns out that I can write it as this diagonal matrix in the middle. That's my B here. And I can write it with a P, 2, 1, 5, minus 1. And then this is the inverse of P, as you can check pretty easily. Remember, to take the inverse of a 2 by 2 matrix, you just divide by the determinant, which in this case is -7. And you're dividing -7 into what you get when you interchange these two guys' main diagonals, -1 and 2. So you have -1 and 2, but then you've divided by -7, so you have 1/7 and -2/7. And then you just negate these guys, but then you're dividing by -7, so you end up just dividing these guys by 7. And so that's clearly the inverse of this matrix. And so there's a good example of two matrices that are similar. This matrix here, A, and this matrix in the middle are the matrices that are similar. And the matrix P isn't that important. In fact, there may be more than one P that makes this true, because you can sort of, for example, if I rescaled this matrix by 2 and then rescaled this one by 1/2, that would all cancel out in the wash. So there's no uniqueness to the matrix P that causes these things to be similar. But here's a basic proposition of the kind that if you go on in mathematics, you'll see it all the time, which is that this has the property of being what's called an equivalence relation. And you know lots of things that have this property. The three properties have names. They're called reflexive, symmetric, and transitive. And they all seem so natural that you might not have noticed them before. So, you know, two things. You know that if A equals B, then B equals A. And you know if A equals B and B equals C, then A equals C. Those are sometimes thought of as just common notions. But it's not so obvious that this existence of an invertible matrix that you can multiply by on one side by it and one side by its inverse, sometimes they're called conjugating by that matrix. It's not so obvious that that satisfies this property. So it actually requires a proof. So here's the proof. So first of all, to show that it's reflexive, I need to find an invertible matrix that converts A to A. Unfortunately, the identity matrix is invertible. So I can always write A as the identity matrix times A, and the inverse of the identity matrix is just the identity matrix, right? So this is just clearly true, and this shows that A twiddles A. So therefore, 1 holds. Now for 2, if A twiddles B, so A twiddles B means that A is equal to P, B, P inverse for some P. I don't have any control over P, it just is what it is. Now I want to somehow write B as in the same kind of way. And well, let's see what I can do with this. I want to isolate B. So the best way to do this is to multiply both sides of this equation by P inverse on the left and P on the right. Right? So this implies that PA P inverse is equal to, actually I guess I want P inverse AP. So P inverse AP is going to be P inverse PB P inverse P, but that's just P inverse times P. That becomes the identity. This is just the identity times B times the identity, which is B. Okay, so what have I shown? I've shown that B is equal to P inverse AP, and that's of the form some invertible matrix times its inverse, right? If you want, you can think about, this being some other matrix, call it R or something, right? So this means that B is equal to R inverse, where R is just the inverse of the matrix the matrix that gets you from B to A, the inverse of that gets you from A to B. Okay, so that's pretty straightforward. And now the transitivity. So for the transitivity, I'm assuming two things. I'm assuming that A is similar to B and B is similar to C. So A is similar to B means that, so there's going to exist matrices P and Q such that, okay, what can I say? A will be PB P inverse, and B will be QC Q inverse, right? Because A is similar to B and B is similar to C. But I can now substitute QC Q inverse in here for B, right? So this implies that A is equal to P times QC Q inverse times P inverse. And now this is just PQ times C times Q inverse P inverse. So now there are two things we want to know here about invertible matrices that we actually do know. If I take the product of two invertible matrices, two invertible square matrices is always invertible. And what's the inverse of PQ? Well, it's Q inverse P inverse. So this is actually equal to the matrix PQ times the matrix C times the matrix inverse of PQ. Okay? And so therefore, by definition, A and C are similar. Okay, so that's why similarity is an equivalence relation. And proofs like this abound later on in mathematics. Now let's see one example of why it would be useful. Notice that this matrix A is actually similar to a diagonal matrix. Okay, so this matrix has 4 entries, 4 non-zero entries. This matrix has 2 non-zero entries. And in general, if you've got bigger matrices, you're replacing n squared non-zero entries, or mostly non-zero entries, with n non-zero entries. And that's usually much easier to understand. So suppose that my matrix A actually represents a monthly update of some sort. And I want to project out 10 years. So 10 years means I want to know what happens when I apply this matrix 120 times in a row. So I really want the 120th power of that matrix. Now, of course, for a 2x2 matrix, you can just ask some computer or calculator even to compute the 120th power of a 2x2 matrix. It won't take it too long. But if you had a 100 by 100 matrix or 200 by 200 matrix, that would be another thing. And there are many situations in which you'd really rather be able to do this in a cleverer way. So notice the following really useful fact. If I know that A is conjugate to a diagonal matrix, so A equals PDP inverse, then A squared is PDP inverse times PDP inverse. Aha! But notice when I regroup this, the P inverse here cancels with the P here. And so I regroup it this way. That's just the identity, and I end up with PD squared P inverse. So in other words, if I want to compute A squared, I can just compute it by computing, and I know what D is. I can just compute D squared and then conjugate it. So this is one of the reasons why we'll want to diagonalize matrices whenever we can. So the same argument shows, just repeating it over and over again, that if I take the nth power of A, then that's going to be a P on the left, a D to the n in the middle, and a P inverse on the right. All the other P inverse pairs just cancel each other out. So what that means then is that if I want to compute A to the 120th, I just need to compute P and then D to the 120th and P inverse. But computing the 120th power of a diagonal matrix is really easy, because when you multiply two diagonal matrices, you just multiply the diagonal entries. And if you want to take the power of a diagonal matrix, you just take the power of each of the diagonal entries, which are the only non-zero entries. And so it's much simpler than usual matrix multiplication. And then you just have to conjugate it by P. So I'd have to take this result and then multiply it on the left by 2, 1, 5, minus 1, and on the right by 1 7th, 1 7th, 5 7ths, minus 2 7ths. But I've got a way to compute very large powers of a matrix very quickly using this process. So this is one reason that we care about similarity and diagonalization. Okay, so here's the next theorem. Suppose that I've got two matrices that are similar. Then A and B will have the same characteristic polynomial. So remember, the characteristic polynomial is the determinant of A minus lambda I, and its roots are the eigenvalues. So if they have two matrices have the same characteristic polynomial, then they have the same eigenvalues and also with the same multiplicities. And here's the proof. 3 lines, not bad. If I know that if I've got an invertible P such that A equals PBB inverse, then I can look at A minus lambda I, that determinant. I'm just using the vertical lines version of the determinant here. That'll be PBP inverse minus lambda times PIP inverse. So notice that when I put an I in the middle, it doesn't change anything, and P times P inverse is the identity. So this is still lambda I, but I've just written it in a funny way so that I can factor it. Remember, with matrices, the matrix multiplication doesn't commute. So you can't just factor things however you want. You have to make sure you always keep things on the left or the right, and that you don't commute two matrices past each other unless you have a special dispensation from some higher authority telling you that you're allowed to do that. So in this case, I want to keep my P's on the left and my P inverse is on the right. So I have P times B minus lambda I times P inverse. So this is really good, because now I can use properties of determinants. So what do I know about determinants? Well, I know that the determinant of the product, determinant of AB, is the determinant of A times the determinant of B. So in this case, the determinant of this three-way product is the determinant of P times the determinant of B minus lambda I times the determinant of P inverse. Now, determinants are just scalars. They're just numbers. So at this point, I can commute all I want. And so in particular, I can move this P inverse over to the other side. And remember that the determinant of the inverse of a matrix is just 1 over the determinant, right? Basically because determinant respects products. So I'll end up with a P times a 1 over P on the left times B minus the determinant of B minus lambda I. This just becomes 1, and so I get the determinant of B minus lambda I here. So the upshot is that the determinant of A minus lambda I, the characteristic polynomial for A, is the same as the characteristic polynomial for B. And I could do it all quite easily without having to get involved in anything quite scary. And so here's my example, right? I have 1, 2, 5, 4, that matrix. We saw that it was similar to 6, 0, 0, minus 1, which is the matrix B. And so now what I want to do is convince you that they have the same characteristic polynomial. This shouldn't be hard, right? So what's the characteristic polynomial of A? Well, I need the determinant. So chi of lambda is the determinant, in this case, of 1 minus lambda, 2, 5, and 4 minus lambda. Okay, 2 by 2 determinants I like because I can compute them easily. So this is going to be 1 minus lambda times 4 minus lambda minus 10. And okay, so I can rearrange the factors in both places, but because it's a minus, this is minus lambda minus 1, minus lambda minus 4, so the minus signs cancel. In any case, I end up with lambda squared minus 5 lambda. And then I'll have plus 4 minus 10 is minus 6. Okay, so that's the characteristic polynomial for A. But you notice that this actually factors really nicely, right? This is actually lambda minus 6 times lambda plus 1. So lambda minus 6 times lambda plus 1, well, that means that the eigenvalues of this matrix, of the matrix A, are 6 and negative 1, right? Because they're the roots of this. And this is also, for a diagonal matrix, the eigenvalues are right on the diagonal, right? So here we can just see that the characteristic polynomial of this should be lambda minus 6 times lambda plus 1. Okay? So the characteristic polynomials of those two matrices are equal. And so let me just quickly define the multiplicity, the algebraic multiplicity of an eigenvalue of lambda. Is it just its multiplicity as a root of chi of lambda? So here I've got two distinct roots, so each of them has multiplicity 1. But things can get a little bit more complicated. And so let's just do one example that's bigger than you would probably ever deal with, but is kind of fun. So suppose I had an 11 by 11 matrix A, and you somehow knew that its characteristic polynomial was computed for you as minus lambda to the 11th plus lambda to the 7th minus lambda cubed. Notice that because this is an odd by odd matrix, the leading coefficient will be negative. And so what do I want to do with this? Well, I want to see if I can factor it. So let's take a different color and say, because I want to figure out what the eigenvalues are. And so what would I get? I'd get that this is equal to, so I can factor out a minus lambda cubed, and I'll end up with lambda to the 8th minus, so there's a typo here. This should have been 2 lambda to the 7th. So make that a 2 minus 2. So then I'll have minus 2 lambda to the 4th plus 1, right? So you can see this was a carefully contrived teacher example to make things work out nicely, because lambda to the 8th minus 2 lambda to the 4th plus 1, you might recognize is the square of something, right? So this is equal to negative lambda cubed times lambda to the 4th minus 1 quantity squared. Okay? All right, so good, so far so good. So now what's that? Well, lambda to the 4th minus 1 is the difference of 2 squares. It's lambda squared plus 1 times lambda squared minus 1. So this is negative lambda cubed times lambda squared minus 1 squared times lambda squared plus 1 squared. And now I've boxed myself into a corner, so I'll move over. I guess I can just write a little lower on this blackboard. Lightboard. So now what do I get? I get negative lambda cubed times, well, this is lambda minus 1 times lambda plus 1, but each of them squared. And then this lambda squared plus 1, I can't factor any further over the real numbers. Okay? So this is the characteristic polynomial. And so what are the multiplicities here? Well, notice that I get lambda 3 times, so that's lambda minus 0. So that means the multiplicity of 0 is 3. Okay, so writing down here, so 0 has multiplicity 3. What other eigenvalues do I have? Looks like 1 is and minus 1 are each eigenvalues of multiplicity 2. So 1 has multiplicity 2, negative 1 also multiplicity 2. And then that's all that there is in the reals, right? Lambda squared plus 1 squared doesn't factor. Let's make sure that this works out, right? We should have, this should be lambda to 11th total. So I've got a cubed here. 3 plus 2 is 7. And then I've got 2 squared, so 4 more there. So that's good. So that must be right. And now, if I were allowed to, in some problems you actually want to allow complex eigenvalues. Those do come up, although we don't discuss them in this course. So in this particular case, you would actually have plus or minus I are both complex eigenvalues of multiplicity 2. But as far as real eigenvalues go, you just have 0 with multiplicity 3, 1 is multiplicity 2, and negative 1 is multiplicity 2. And knowing what the multiplicity of an eigenvalue is can be very useful in figuring out whether, for example, a matrix can be diagonalized. So that's it for video lecture F4. Thank you very much for your kind attention.